Eric's lecture. And to prevent that from happening, I will take the first 10 minutes and tell me when 10 minutes is over, because it's just not worth it to cut your time back 1 minute. All right, so yesterday we had a nice qualitative soft introduction to what quadruples are, and today I just want to spend a few minutes talking to you. The slides will be posted or have been, and there was a slight notation, correction. Told you about all these dynamics, but I didn't say much. The one thing I didn't do from the qualitative thing when I suddenly ran out of the room at 2 p.m. is to tell you that it's good to be aware that these quadrupolar systems, and that coupling is large enough. The coupling is large enough that you can use spectroscopy at zero field very conveniently. People do a lot of different kinds of zero field spectroscopy these days, and it's considered still a pretty exotic topic. But I'm just saying this because you're being talked to for it. And if you like that kind of off the beaten path thing, nuclear quadrupole resonance is something with practical implications. It's also sort of interesting to think about. All right, so what I want to spend just 10 minutes on is to point out that when you have spin quantum number, the angular momentum is greater than 1/2, and it's not a two-level system. So those density matrices and the matrices that represent your operators and everything are going to take a different form. They have more levels. Okay, so our quantized states look like 1/3 vectors. Make sense? It's always going to have the same I equals 1, but what is m sub z, or m? Well, it's either 1 minus 1 or 0. So the meaning of, for example, this column vector is that there is no spin or magnetic moment in the z direction. You could measure it and you would get 0. That's what that means. It doesn't. It's not x, y, z. It's +1, 0, and minus. Now we can make a lot of matrices. How many matrices do we think we'll have in this space? We used to do matrices for the spin 1/2. I think it was a 2x2 matrix. And how many different matrices that were linearly independent did you have? And price square, which is like normalization, like unity. So how many? 4, and there are 4 entries in a 2x2, and that's not a coincidence. So now we have a 3x3. So how many different kinds of things are there for I equals 1 spin? Different kinds of measurables, different kinds of states that we can create, different kinds of operators. How many are we expecting to have? 9. Of which 1 is just going to be unity, so it's kind of not a thing, but it's a thing, but it's not a thing. All right, so the first one, sorry, I didn't read this to you. The first one measures IV. So it's going to be because our basis set is all about IV. And you just put the expectation value on the diagonal. Everybody good with that? Then that would be density matrix for something that's all organized according to C that has a net polarization along Z and over S. That would be a density matrix. It might have a constant out front. And if you wanted a matrix representation of an experiment in which you try to measure along Z, that matrix would also. So this is a matrix like 1 element in a basis set, 9 basis set. We use them both for the operators that represent measurements or evolution or energies, and we use them also for the states of the system itself, normalized states of the system. So that's Z. Measuring Z, if it's an operator, organized along Z if it is. Okay, another one that we know we're going to need is the unit. Unity. So measuring total angular momentum, and in a way you could just say it has the eigenvalue for I, not M, on the diagonal. And that's just an obvious thing. So now that's 2 matrices out of 9. How about just thinking about populations always have entries on the diagonal and nothing off of the diagonal. Does that make sense? On what we do with spin 1/2. Okay, so there's got to be a third population, another way to populate. And this also comes up in a couple spins where you have things like dipolar order. So there's a thing that you can find just by saying what's orthogonal to both those. You could take that approach, and I'm going to belabor it because I want to get correct on this quickly as possible. If you say what's orthogonal to this and orthogonal to this, you come up with something that looks like this. That means I'd be like underpopulated on the outer level and overpopulated in the middle, or the reverse. You could do the reverse. So when we talk about that as being a density matrix, it's called quadrupolar order. When we talk about that as being an energy curve or a measurement, that's the quadrupolar coupling. And previously, we had another expression for the quadrupolar coupling in the last lecture. And if you work it through, you can see that this is indeed equivalent to I squared minus 2x. Okay. So that's the third kind of population. Now, I've already illustrated here that you can find the rest of them using some tricks. One is just to ask, well, what's linearly independent? Another is to say, what can I get if I start doing arithmetic with the ones I already have? These are always good moves. If you had a new spin system, if somebody said on a midterm, but nobody did, but somebody said, get me the full set for I equals 3/2. Those are the kind of games you could play when you found them. Now, another thing is you always want to use diodes and I, because that's what we measure in a receiver. And the way you make those is the same way we should have done for I equals 1/2, but I don't remember if we did or not. And that is they are constructed out of I plus minus. And we know how to, just by inspection, make I plus and I minus. Yep, there's I plus and there's I minus. And then if we have those two guys, we can rearrange them to make I. Okay. So now we ask, how many single quantum coherences are there in this space? So we're missing some single quantum coherence. And yeah, because there are 4 places that are one off the diagonal. You think about that 3x3 matrix. So we got to have 4 different things that are like single quantum coherence. And just like what happened with the populations, what we're going to end up doing is making things that are sort of X-like for one level pair, but minus X-like for the other pair. So these matrices are different from X and Y. X and Y had opposite signs like here and here. This has opposite signs here and here, and it's kind of saying I'm X for the upper level and minus X for the lower level, something like that. Anyway, with those 2 and X and Y, now you span the full space of things that are one off the diagonal. And those are called QX and QY coherences. So they're coherences. I don't know how they relate to an energy measurement or a Hamiltonian term off the top of my head. But they surely do come up. Finally, the only entries we have used here, we did everything we could do with the populations on the diagonal. We just did everything we could do with that, but we have these 2 left. So those could help you make double quantum type coherences. And there are 2 such double quantum coherences. So one of them you just make up out of thin air. You say, well, what if I put a 1 in each place? And then you say, well, what's your relation dependent? And now you have 9. You have 9 things, so you span the space. One of the things when you're doing this, you should ask yourself, are they all orthogonal, really? You can do that by yourself, and if you can't, you can ask this. I belabor this because you're going to encounter this for another spin, and now you know the way to kind of approach it and think it. You also should check that they're all normalized, and the norm of these things should be I times I plus 1. That's different than, like, I mean, that's a general rule for all spins. So you'll have a different particular normalization than spin 1/2. Everything has to be size to 2. Okay, so rotations are constructed the same way as spin 1/2. It's e to the I, and then the operator for that angular momentum. When I rotate around Z, I exponentiate the operator. See, so I can make the rotate, all the rotations that way. And so you can look through these notes and see how they come out and see if you have questions about that. Those are rotation operators. So you could write a Hamiltonian for chemical shift. It's the same thing. It's like the magnitude out in front or whatever the shift is, and then an IZ operator. And you could even construct an echo pulse sequence because you could write an operator for the pulse with these tools. And you crank it through without defining product operators. It's the same as before. I start with Z magnetization. Then I might want to rotate it using a pulse, and that pulse might be at 90x. So this was a rotation around x that is on a previous slide. You can look at that. And so it's still a bilinear operation to rotate this. And then you're going to get a resultant. And you probably don't want to do that by hand. You can use Mathematica, or nowadays you can ask Claude to do it for you, or ChatGPT. Anyway, you'll find out that that rotation, if you put 90 degrees in, returns just what you think it should. It returns IY. And if you put a generalized angle, it returns an adjacent from Z to minus Y and around back. So that's just the thing that's figuring out. Is that a question? Chris? No. Okay. So a lot of things are the same. And this will be general for other systems as well, this approach of checking things. But not every bit of your intuition will be correct. And I'm going to just mention one thing that doesn't turn out the way you think it would. And then I'll leave the rest of the slide deck for you to look like this. So that's a rhetorical question. When I did this problem, I acted like nothing happens when you turn the RF on. This represents the RF, this rotation around X. And I acted like there's no other Hamiltonian on during that period. And I asked you the question, do you think that's going to be realistic? How would you answer? Is it really realistic? Is that reasonable? We do this all the time, right? These are idealized 5 pulses, idealized 5 ID pulses, but how do you know whether they're reasonable or silly?
You just have the higher pulse and then you transform the thing that's already high frequency to
Other interactions.
Yeah.
Yeah.
But that's all in the sorry.
No, okay, yeah, no, I hear you, I hear everything you're saying, that's fine. But what makes it reasonable to say, I ignore all that other stuff? Don't overthink it, this is not an advanced question. If that other stuff is weaker than your pulse. Well, it's not, it's not. So I did it anyway for you, just to illustrate how these things work, but this is one of the things about any quadrupole, other than maybe sometimes deuterium and lithium, it's not. But sometimes we have to do that anyway. So I say, besides propagating the density matrix with exponentiated Hamiltonian, how else could we have predicted the evolution? Is there another tool you learned? We have to grind that up. Anybody remember anything? You could use finger physics. Yeah, Chris, except that this was an exercise to see if that's right. This was an exercise to see if that's okay, because not everything is okay. So, well, you want something else in this class. What else could you do? It's sort of, yeah. I mean, that's like if Anne's asking a question just hysterical. No, remember we taught single and double conjugators and used the thing called the Baker-Towns or Gamble. Okay. So you can see if you run some conjugators, whether it's just going to be a normal cyclic permutation between this and circle on that one. And yes, you should probably start using tools. Now, what you can do for yourself is to try to model an echo. You could try to put chemical shift evolution and then a 180 and see if it works normal. And I'll tell you that it should. Just see if you can use these matrices and do an echo. And the echo should be well behaved, should be normal. However, that's not reasonable for almost any system, there's just like very few systems where you have a quadrupole and it would be dominated by CS. That's special, unusual, doesn't come up. So, I mean, I could make a case for you that's like that, but don't expect it. Just end up in your sample sheet. So a more reasonable thing to be doing is to say, when it evolved under the quadrupole Hamiltonian, and I'm going to use the first order quadrupole, and I gave you that Hamiltonian already. And then I want to refocus that. And why are we doing an echo? You remember from yesterday? Why are we doing echoes all the time?
This guy is really focused on.
There's a lot of offset, and there's a lot of information. This is a really broad spectrum. And if you have trouble getting a undistorted broad spectrum, you should always think of the possibility of echo. Now, if your teaching is real short, you're not lucky. But if the teaching is long enough, you should always think of an echo if you have a broad spectrum opposed to distorted. There are other things you could do, but that's something that should have occurred to you. All right, so you're going to do an echo. You're going to have quadrupole interaction be the main reason that they are evolving, which is sort of what happens in deuterium. So we're going to make an echo sequence. And this is the last thing I'm going to leave you with, that so first it evolves, but when it evolves, it starts I'm starting you off with Y magnetization, because I'm saying the pulse already happened. I'm evolving under the influence not of this chemical shift, but the quadrupole interaction, and that's different. That has negatives on the outside ones and double that frequency, but positive in the middle. Not a chemical shift, quadrupole interaction. So starts with IY, evolve under the quadrupole, and what you get later is interesting. It looks like IY, but it doesn't evolve over to IX, it evolves over to this other thing that I call. Okay, so it makes an interesting, funny thing. You cannot detect in your receiver. So even if you go to the other channel, you're not going to see it detected.
It looks like the iOS carries a negative sign in the beginning, whereas previously it had plus iOS costs.
Well, is that right?
And depending on where you're.
It should start on minus IY. Yeah.
Okay.
But it's evolving to make a different thing. And I already said all of that. But here's the really weird thing, and the part of this that I want you to hopefully remember is that if you try to detect it with an echo, if you run this out, if you choose to do this homework and turn it in, maybe like, let's say after the midterm, we can have a couple of quadrupole homework problems. If you try doing a 180 to refocus it, you'll have to see how a 180 behaves with your IY. You wouldn't want a 180Y on an IY, you probably want a 180X. But how does that 180X or Y behave on this quadrupole reverse? Does it flip it normally? Does it move it by 180? Does that cause an echo to form later? It's a hypothesis. And the answer, if you do this homework later, I'll tell you what the answer is so that maybe that's less frustrating to work through it and you can see what's coming up. The 180 in this scenario doesn't do what your intuition says it would do. So you know what the length of a 180 is, you confirm that when you do the initial pulse. But on these systems, it's going to act as if it's a full 2-pi rotation. So what that means is that in practice, when we do an echo for a quadrupolar system, we use a different 180, shorter, like a 90. So it's a 90-90 refocus sequence. And this homework problem, should you choose to go ahead and do it, will help you get a good feeling for why all the pulse sequences look like. So you use a 90Y to flip the sign of the quadrupolar coherence. And that's just one example of weirdness in these pulse sequences. So if you, in practice, want to do some deuterium NMR, or you want to do other, things or whatever, you just have to be aware of that. You know, some students kind of stumble in and think, well, P2 cos theta, so it's probably like everything's probably like this big one out, and I'll fit up. This is your heads up. The literature will tell you what's different, but you can also do these kind of calculations and understand it for yourself. And I think, even though there's a lot more in here, I think I would like to stop there and give you the whole slide deck, so you're welcome to look through it and think about it, and it segues into how to set up the levels for rehabs. But I think our class time is better spent if we transition that, and you're welcome to come up, and then you have this deck here. You choose to do that, no problem, you can ask me. Okay? Any questions or thoughts right now? Yeah. Hi.
I was wondering, so you use this terminology, first in one, which is overtone.
Yes.
What does that refer to?
The excitation, that would be two
How do you?
levels, meaning two quanta of angular momentum. And it's weak, meaning you need a lot more V1 to excite it, and you expect a very weak signal. Why is it allowed at all? Which is it?
Formally forbidden transition.
It's forbidden. It absolutely is forbidden. And it's I think of it together with transitions that happen in the long geometry. So for EPR, we see these transitions as being sometimes almost as strong as the allowed ones. For NMR, we almost only could see them for super strong couplings or super strong quadruples. And what's making them a little bit allowed is these strong interactions that mean that you're not really in pure Zeeman.
The stronger the EFG gets,
The more you might have it feel up. But because it takes a lot of power and correspondingly long pulse times, a lot of times a little bit of intensity you wouldn't have gotten basically dephased. So it's a very frustrating thing to try to do either these so-called parallel mode or overtone set. Very, very. Yeah, so it's you're not in the high field limit. So any things that are not supposed to be allowed. I used to wonder if the systems where we were doing polarization effects. So you have these paramagnetic states in between that you want to manipulate, and they may be kind of things like that. I mean, there may be sort of like off the beat path states or examples where you could try that, but most of the things that we designed to do normal NMR are just not. And it's attractive for reasons I think are probably baked into your lecture. Like, why would you want to go to that? Well, I think this comes up there. Why is there a second on that sometimes in the ENC? I think the answer to that is coming up. Other questions, other thoughts? Great. So there's a lot to do here in spectroscopy. We didn't get a chance to get it all as to, but if this interests you, we can talk about it more later, or you can do your paper up. While Eric's setting up, I want to ask about an idea I had that a handful of people who are going to do a paper or doing this class for a grade. I'm wondering if it would interest you to have a session just before you turn your paper in, where we do a go around like what your paper's about and what you're encountering and the literature that interests you and what's frustrating about it, and you may enjoy hearing what each other is really paper on, rather. Does that sound good? I'm not sure when this would be on the schedule, but it could be the tail end. Maybe not next week because you're going to be in the middle of your, maybe the week after that, maybe good. Like after the exams do something like that. Yeah. Okay, so I'll discuss it with the other instructors if you guys think that would be helpful. We've been using this. USB-C hookup rather than the HDMI.
So presumably for stereo, overall transmission, particularly ineffective.
Yeah, it is, but it is not very effective. But where I did see it a lot, and I think it holds some potential for our field is midfield instruments at N14. Because that's a bigger one, right? And also it's very broad unless it's a service in a different site, so the overtone. The thing that Eric's gonna talk about, that overtone is narrow, it's really important. And nitrogen N14, it just seems very inviting, right? Definitely N14, we want to measure them. Okay. Now, this is sort of a funny deal where almost everyone here already knows Eric super well, but then there might be one person on the internet. So if you want to tell them a little bit about your academic background before you start, that might be helpful. Is there anything I can help you with?
I think we're good now.
Yeah.
I don't want to hide this. I'll just put it over there.
And there's something to make go away.
Oh.
Another thing. Thank you. Yeah, so if you just want to tell them.
Yeah, so I had a slide on it.
Okay, good.
And I think I'll put these slides, I'll get them to you later today. I just haven't gotten there yet. There we go. So me, all around. So I'm a scientist here at NYSDC. I do solid state NMR. And so any solid state NMR questions you have, I pointed it. Yeah, solid state NMR questions you have, I'm the guy here. I started out, almost quite a long time ago, doing NMR in the lab of Philip Grandinetti at Ohio State. Got my BS in chemistry there. In 2012, I focused on experiments doing chemical shift anisotropy measurements in modified silicate glasses using a technique called magic angle flipping NMR. We'll talk about something that's similar to that. We can talk about it. It's an interesting little experiment. I then went and did my PhD in the lab of Griffin at MIT, where I looked at using oxygen-17 NMR, study peptide and protein samples as a tool for another dimension in multi-dimensional correlation spectroscopy. After that, I joined Ann McDermott's lab at Columbia, looking at the measurement of millisecond and microsecond motions in proteins. And so I'm going to talk a little bit about what I did primarily, for my PhD. Despite the fact that you might think that I did that as an undergraduate with Philip Grandinetti, it's a well-known name, quadrupolar NMR, and a lot of the slides you'll see are things that I learned when I was in his lab before I moved to that. So just, I think Anne probably showed you something similar here that shows the different NMR active nuclei. Most of them happen to be spin greater than 1/2. So in some ways, we're kind of lucky that in biosolids, carbon and N15 are both spin half, and proton is. We've got lots of luck there that we have 3 highly abundant in the protein molecules that we can probe that have spin half nuclei. If you look at how many spin half nuclei versus spin greater than half, I don't think this one actually shows that specifically, but
Yeah, but it has a lot of information. That's probably a better one to keep if you wanted to keep one on your desktop. Because it's got all the information.
So just a few examples, kind of some prominent nuclei that are quadrupolar, so spin greater than 1/2. So deuterium is spin 1, and talk a lot about that. Each row is common one. It has a quadrupolar coupling, which Anne talked about, around 0.23 megahertz, so about 230 kilohertz in water. You also have lithium-7, which is also spin 1. It has similar size quadrupole is 7 spin 1 or 6 spin 1. I always get them confused. 6 or spin 1, 7 is the spin 3 halves and has a small CQ. So you'll see a lot of papers where they look at lithium 7 or lithium 6.
Because the table has a typo and it has a bullet 7, that's what.
Yeah, that is why it's confusing. They both, one of those should stay 6 and one should stay 7. Boron 11 is one you'll see in a lot of papers on things like zeolites or glasses. And it has a moderately sized CQ, around 3 megahertz for a, spin greater than 1. In the 14, they were talking about that, also a spin 1, because you can see it has a very large CQ, so you don't see as much in 14 NMR, despite the fact that it's very, very natural abundant. So there's a lot of it in our proteins. If you don't label within 15, it's almost all in 14. But it's very difficult, and as Nish was saying, people try to do something called overtone spectroscopy to detect it because the line is so broad and it's so difficult. And one of the things is that you'll see some of the examples here have much larger quadrupole couplings than N15, but N14, because N14 is spin 1, there's no central transition, which we'll talk about, which eases the ability to measure something like oxygen 17, which has quadrupole couplings from around 5 to 15 megahertz. And so the ability to excite that entire bandwidth, like you have to do in a spin 1 nuclei, is very outside the range of the capabilities of our equipment. Exciting at 3 megahertz broad bands is very difficult. So sodium is another common one, and aluminum 27 you'll see quite often in material science. And then you'll see some chlorine 35 and chlorine 37 work. Yeah, which have massive. So you'll see this particularly out of a lot of the late Rob Sherko. His lab did a lot of this work on pharmaceuticals, looking at the chlorine in some pharmaceutical compounds and characterizing that. So it's
It's kind of saved by the fact that very, very often near octahedral symmetry.
Yeah.
So
yeah. So if you were looking at something that was very non-symmetric, you would have a lot of trouble. A lot of these compounds are fairly good examples of kind of the middle point of what you can get. So in chlorine, you get way higher than 60 megahertz. You don't get much in the small 10s or teens. Okay. Yes.
This will be like in this table you don't have angle standard. Roaming
yeah, I don't
know why.
It's also big.
It's
How big is it? It's big.
So yeah, that's probably, if you do any solid state NMR, the most common quadrupole nuclei you will interact with is potassium bromide, bromine 79, which we use to set the angle. Because of its near octahedral symmetry, it has a very narrow line with a very, very small quadrupole coupling, but you get these very strong sideband interactions when you're close to the magic angle because of its near octahedral symmetry.
the sideband, the quadrupole plus the 10 to 6.
It's going to be mostly CFA actually, but yeah, in that case.
It's big like chlorine. I just don't know the exact number.
I have a list that has all of them. This one's just truncated things. So the big thing is that this is more a list of things you'll see in the literature, people doing like actual studies on. Outside of potassium bromide, you don't see anybody really doing anything with bromine 79 or bromine either too. Okay, so in these quadrupole nuclei, we have this quadrupole interaction. I think Anne showed you something similar to this, where it's an interaction that we describe, a Hamiltonian, where it's I interacting with I, so it's a self interaction, and we're describing mostly what is considered the electric field gradient of tensor. So in the nuclei, we have a quadrupolar moment. That moment interacts with the electrons in the nucleus and creates a field gradient essentially. So there's essentially a gradient field, and that's what we actually measure is that interaction. We're not really measuring the quadrupolar moment, or in our experiments. And so we describe it using similar terms, as a tensor as we would any other tensor, like the CSA or the dipole. If you look at dipole as a full tensor instead of just a single uniaxial piece. And so we define two things, the quadrupolar coupling constant, which is essentially just a scaled version of the largest of the electric field gradient tensor principal axes. So it's just the VZ component, and then an asymmetry, which is defined similarly to how you define the asymmetry in CSA, except for, this switch XXYY here, where it's XX minus YY instead of YY minus XX, and that's just due to convention being that you define them by their magnitudes as ZZ greater than XX greater than YY and EFG, and that's just historical. So in this, you can think about it like a, as Anne described, I think yesterday, a cigar or a frisbee in space, some sort of asymmetric shape that exists in space similar to a CSA, and its components will then change how things look. So if we have something that's spin 5 halves, like oxygen 17, it's spin 5 halves. So instead of just, when you put it into a magnetic field, instead of just having a splitting where you have 2-1 transition from, minus half to half, you now have energy levels at 5 halves, minus 5 halves, minus 3 halves, minus a half, 1 half, 3 halves, and 5 halves. And all of these, just with the B naught interaction, you have symmetric energy levels, and then you add in the quadrupolar interaction, and suddenly these energy levels are no longer perfectly symmetric, and then this is just first order, and then if you have second order quadrupolar, they move a little bit again around, and so you end up with this much more complicated energy level diagram for something like spin 5 halves. So you have 3 halves, you just wouldn't have ones. You have 7 halves or 9 halves, you have even more energy levels. You need more transitions that can be excited instead of just one. In the case of a spin 1 nuclei, you have the 2. And this, while it seems like now all hope is lost, like cheering was hard enough, you got this huge line, like how are we going to do anything with what we have? And I'll talk a little bit about that in a minute, but I'm going to kind of introduce a slightly new way of thinking about the transitions, just because it makes it a little bit easier visually, and in this lecture to talk about the experiments. So if we consider each NMR transition, all of those that we saw in the previous one, all see as existing in the sum of multiple components, that each component has 3 different parts: a strength, a spatial function, and a spin transition function. So instead of thinking about it just in terms of what you've been looking at, think about it a little bit more as broken down into different terms. And so then we can think about how we can manipulate spatially and how we can manipulate spin transition to do experiments, instead of just thinking about how the spin transitions work. There's a spatial component that's in there, and you talk about it in a similar way. I'm just going to break it out in a little bit of a different type of thing. So one thing to think about is the spatial component. So the spatial functions inside these transitions are proportional to tensors of rank L. And then the spatial symmetry of those functions is determined by the spatial symmetry of that tensor. And so then we express this using the L rank Legendre polynomial for that spatial system. So something with rank 1 would have spatial symmetry at 90 degrees, and so rank 2 you have 54.74. That's the point at which the Legendre polynomial will be 0 on that cos theta. And so this is an angle that you've probably heard about. We call it the matched angle. Technically, only the matched angle for rank 2 tensors. Those tensors happen to be things like dipole and CFA. However, quadrupolar tensor is not a rank 2 tensor, and so that's going to be a problem. This is why when you spin deuterium, you don't get one single narrow line, you get a bunch of side bands. So then rank 3, you have these other angles, and then rank 4, you have 2 angles. So as you get to rank 3 and 4 and higher, you start to get multiple angles between 0 and 90 that will effectuate a 0 point if you spin at them. So 30.56 and 70.12 for the rank 4. Okay, so what is the quadrupolar interaction? what frequency contributions look like. Okay, so first order is just going to be your nuclear shielding, so that has your isotropic and your D, your F and your D, and then you have first order quadrupole. This has D symmetry, spatial symmetry, so S, a D, and then second order quadrupole. And so this has S, D, and G spatial symmetries. So in the case of your nuclear shielding, you have your isotropic and your CFA essentially. And so your isotropic has rank 1 spatial symmetry, and so it doesn't go away when we set it the magic angle. You still have an isotropic chemical shift. You don't get rid of that. Still exists. If you don't set a magic angle, you continue to have CFA of varying degrees depending on what angle you're at. Won't always be 1, can be different than that. So it doesn't matter what angle you're at as far as what your CFA looks like. Okay, so what does this mean when we look at what we're doing? So we have isotropic components here, and actually down here in the second order quadrupole. So for deuterium, we really only looked at first order quadrupole. The second order doesn't really come into play because of the lack of multiple transitions. And so this is on the order of megahertz. Whereas, the CFA and the second order quadrupole is generally on the order of kilohertz. So this is a good thing. If we can eliminate the first order quadrupole interaction, we might have a chance to do spectroscopy on it without some sort of crazy machine where we have to pulse at megahertz strong beats. You will have an isotropic component from both your chemical shift and from your quadrupole. And so if we want high resolution, we want to get rid of all the anisotropic, which I've shown in red here. So the anisotropic components here are in red. And we want to get rid of those if we want narrow lines. So our narrow isotropic lines like we're used to in solution or in standard MAS happen. So how do we do that? Well, generally what we think about doing that, we exploit the spatial symmetry to get rid of our anisotropic interactions because that's what we've been doing with spin and half nucleus. So let's just spin. So what happens? We spin and we get, these spinning sideband contributions, and you get, the zeroth order contribution. And so if we spin, we want to try to find an angle that we can spin out all of these interactions. Unfortunately, if we spin at the magic angle, we get rid of all of these. Great, we're happy, but not this. That's not good. We can spin fast enough. I mean, obviously, this is only we're only going to get rid of this. We're going to spin fast enough that we're getting rid of the megahertz. That's why it doesn't completely go away. You get spinning 5 into deuterium, but they still exist because you still have residual couplings from the spinning sidebands. Until you spin out much higher than the interaction strength, you don't get perfectly narrow single lines. But the problem is that if we spin at the magic angle, we still have this contribution from the second order quadrupole that has this G spatial symmetry and a C4 spin symmetry. And what does that look like in the real world? So in the real world, if we just take a quadrupole and we can excite the whole thing, we get a spectrum like this, that. You get this narrow central transition and this very broad, notice the line here is in megahertz. Broad 2 times the quadrupolar frequency breadth line. But yeah, so this is blown up to 46 times here. So that's this what I'm right there is that. And so then if you only look at the central transition, then you get this. If you only do the central transition simulation, you get this simulation. If you do the whole thing, you get this. But all of the these satellite transition interactions are right here at 1/2 to 3/2 and 3/2 to 1/2 instead of just the central 1/2 to 1/2 transition.
So you guys are looking at scale, right? Like that narrow center thing, it's so narrow. 15 kilohertz.
Yeah. Okay, so then what happens when we spin? Well, we get a spectrum that looks like this. So looks pretty similar. And then when we zoom in, it's just a bunch of these very tiny spinning sidebands broken up on that. And then if you look at just the central transition, well, we're narrower. Now we're talking about, sub 10 kilohertz broad line, but it's not a single line. It still has a line shape. So why? Why aren't we just a narrow line? Why is it still fluorescent? Why is it still so broad? Well, we haven't gotten rid of that G spatial symmetry. So that residual second order quadrupolar line broadening that exists. So this is just an example in the real world. We have a spin 1/2. This is just a carbon. We have, a stationary or non-spinning sample that looks like this. You have, all of the carbons under this big envelope. If we spin, we get all the peaks broken out nice and narrow. Say we look at something like an oxygen 17 labeled protected amino acid here, leucine, you get a non-spinning spectrum. It's about 700 ppm broad. There's 2 peaks in here, but it's hard to tell. You kind of need to know what they are to be able to fit anything about this. If we spin, we narrow these out, but we still have 2 fairly broad peaks and spinning sidebands boot on top of it. And this residual line is due to the second order quadrupolar. So we're landing here on this curve, and so there's still this spatial symmetry still has a non-zero value, still narrow somewhat from what you'd expect if you weren't. But if we could spin at say 30.56 or 70.12 degrees, we would get rid of that interaction, that second order quadrupolar interaction, but we would reintroduce our CSA and dipole interaction, so we wouldn't necessarily then get a narrow line, you'd get something different that's broad. Okay, so one important thing to think about is that we're just exciting the central transition here when we look at it. So that's what I'm talking about. So we're just going to excite the central transition. Now we don't have to worry about that really, really broad spectrum. So we've eliminated all the first order quadrupolar interactions. The spin transition is 0 for all m minus n transitions. So we've eliminated that using spin because we're doing a central transition. Now here's the question. How do we selectively excite just the central transition? Does anybody have any idea? No, I mean, it's kind of, so it actually turns out we're just one. So the central transition is really narrow, and we have very weak pulses in comparison to the large bandwidth. And so it just works selectively like you would a selective pulse, like if you wanted to just pulse on COs. And you use a much smaller on resonance pulse. So we're going to be on resonance with the central transition, the close to the central transition. And then we're going to excite it with a relatively weak pulse in comparison to quadrupolar interaction. So something on the order of kilohertz instead of megahertz. And we won't see much of these satellite transitions because we won't be able to excite that transition. Essentially, we've gotten lucky that the central transition happens to narrow enough that we can hit it with our pulse, such that the other transitions are much broader. So once we have just the central transition, we actually can just treat it like a spin half nuclei. So we can just treat it like a spin half, like a pseudo spin half nuclei that just has a really broad line. So spectroscopically, we can hit it with all the pulse sequences we would with a spin half nuclei. So we can use our standard echo. We can use everything that we like in spectroscopy, but with a few caveats. We have a broad line, and then there's going to be some things that don't work quite as well because of the large interaction that's happening during the pulses and during waiting times and such. So how does this look in practice? So much like a static or non-spinning spectrum of a spin half nucleus, there's a lot of structural information in the central transition spectrum with that breadth. So there's a lot of structural information that's in there. As we increase the quadrupolar coupling, you can see this line gets broader, makes it harder to detect. So in the real world, constant integrated intensity, you want something really small. 1 megahertz, you've got a fairly narrow line, it almost looks Lorentzian. As we get bigger and bigger and bigger in this sort of simulation, you see that this line shape coming out, and you can start seeing the spinning sidebands, and in comparison to the amount of signal you have under the seat, the same intensity, but you can barely see the spectrum anymore at 10 megahertz. And then similarly, if you look at different asymmetry parameters, you can see that this line shape changes just like you would expect, like a static line in a standard NMR. And so then how do we extract this information out of these experiments? Well, we're going to use a lot of simulations to do that, but this is something that Anne was just talking about. So one really important thing about actual practical spectroscopy on a spin 1/2 is that your applied B1 field, if it's not much larger than the EFG, than the electric field gradient, the effective mutation frequency will be shorter than expected. So this is kind of similar to what she was saying with, that pi pulse not acting like a pi pulse on the quadrupole. Well, it's true just in terms of how does your nuclei mutate across a pulse. So if you just apply a pulse, if you're talking about something that's like a solution, so quadrupolar solution is going to have a very small CQ, EFG, because it's tumbling and that averages a little bit away. So you'll only have chemical shift and quadrupolar shift. Something to always not forget about is that there's always shift. There's always a shift in the quadrupolar nucleus. It exists all the time. It's isotropic, and it shifts away from the true chemical shift. And so you will get this kind of purple line if you're able to pulse much harder than sort of lightish purplish pinkish line. So 1 kilohertz quadrupole when we're pulsing at 50 kilohertz, and you get a good mutation where your 90 pulses at 5, 180 at 10, 270 at 15, and then again your 360 at 20 microseconds. So what happens if suddenly the CQ is equal? So 50 kilohertz CQ, 50 kilohertz pulse. Now you're looking at something around 3.5 or 4 microsecond 90. You're passing through 180, around 8 or so microseconds. 270 around 12.5 or 13. And then, for the 360, the 270 is around 11. And so, as you can see, this not only is it shifted, but also you don't recover down to -1 or even get 1 on your pulse. You're slightly smaller. And then even down here, you're not getting back to equal intensity on your 270 as you have on your 90 pulse. And as you go even higher, then that kind of evens out. So you get into this weird space where you have sort of modulations because the interactions are the same magnitude, or near the same magnitude. And so then if you have a very strong quadrupolar coupling, which is where we'll generally be operating for a spin half nuclei, something in the order of megahertz, and you only have 50 or maybe 100 kilohertz strong pulse. And so then you get this red line where essentially you have on this 3 halves what looks like 100 kilohertz pulse instead of a 50 kilohertz pulse. And so then if your mutation frequency, if your omega 1 is much, much less than your omega Q, the effective central transition frequency becomes I plus 1/2 times omega 1. So your omega 1, your effective mutation, so your effective omega 1 is going to be for 3 halves, it's 2 times omega 1. For a 5 halves, it's going to be even stronger. And so you have effectively much stronger pulses, much faster mutation frequencies than you would have in the case of the spin 1/2 nuclei. And this is just something to think about when you're setting up your experiments on a quadrupolar. Yes.
So here you increase the CQ, the intensity of the transition, max intensity also going down.
Yes.
Which means that so evolving into other terms in the density matrix, that was happening to these CQ.
Yeah, it should be. So yeah. Effectively, you have less intensity in your as your CQ gets larger, but you're able to pulse it much harder effectively. So much shorter pulses, which in some ways is advantageous. So how do we obtain isotropic spectra out of our quadrupolar coupling? We really want those narrow lines. We want site-specific resolution. We don't want, 5 kilohertz broad lines overlapping one another. That make it hard to do any sort of actual spectroscopy on real complicated samples that have more than one site in them. So one way is we're going to need a bigger magnet. So if you, I should have put it up here, but if you can recall back what the equations look like, I should have highlighted it then. Just go back so that, take a look at that. Okay. So if you look back at what these are like, you can see that the second order quadrupolar interaction, it scales as 1 over omega naught, so 1 over the strength of the magnetic field that we put it in. So unlike our CFA, which scales with that, so we can use a larger magnetic field to make a narrower line. So we just need a big magnetic field. So let's just build a bigger magnet. We'll call up Rupert and we'll tell him we want a much bigger magnet. So we want to be able to look at isotropic lines. So here, this is a aluminum 27, which is another spin 5 half nucleus in this aluminum borate sample. And so at 600 megahertz, 14 Tesla, you get a spectrum that looks like this top one. And then as you go up to 1.7 gigahertz or 1700 megahertz, 40 Tesla, you can see that you recover perfect isolation of the 4 different peaks in that sample, whereas at 600 megahertz they're almost fully overlapped. One big advantage they have here is that the CSA of the aluminum 27s are very small, so you're not seeing a lot of spinning side bands like you might see in something like oxygen 17, which we'll look at a little bit, but later. But so in this case, we're going to need a bigger magnet, but how much money do we have that we can buy a bigger magnet? 1.7 gigahertz is a pretty big magnet.
This is I think the most dramatic thing in all of NMR that happens with field is going from kind of like a mountain range where you have no idea what's what, and you don't even trust the simulations that much, even if you're really good at them. And then you have like 80 per chemical. It's night and day, and nothing. I mean, everything gets better with the field, but nothing is like this.
Yeah, the one over omega naught tendency is really helpful. Only it can be 1 over omega naught squared in the mean side.
You don't listen when they ask for different physics. They never listen.
Okay, well, we don't have that much money, so we can't just buy a big magnet. Even though we have lots of big magnets here, they're still not big enough. So what else can we do? Well, we can exploit spatial symmetry. So we can imagine some geometry to utilize where we average both the second and fourth rank anisotropy in the same experiment before obtaining the spectrum. And then we'll get a spectrum that looks like a spin 1/2. So how can we do this? Well, we can imagine a rotor where we can spin at 2 different angles simultaneously. We can imagine what is dubbed the double rotation experiment, or DOR, where you have an outer rotor that spins with respect to the magic angle, standard magic angle, and inside that rotor, you have a second rotor, smaller rotor, that spins independently at 30.56 degrees off of the axis of the original rotor. So inside this rotor, you have essentially this big rotor and got some holes in it for pneumatic air to go inside the second rotor to spin the second rotor. So you have 2 spinners, one inside the other, and then you can just apply pi over 2 pulse, the 90 pulse, and acquire a spectrum with an isotropic peak, and then all these spinning side bands, some of them are negative because it does really weird things, and you spin at 2 angles, and you get some really weird effects on the spinning side. But and so then the one drawback of this experiment is, well, you can't spin very fast if you have to put one rotor inside another. And so the commercial double rotation probes that existed had a 14 millimeter outer spinner with like a 4 or 5 millimeter inner spinner. And then the other big problem you have is that your filling factor is very poor. One, you're filling at a strange angle to your coil, because your coil is wrapped around this outer, and you have a 14 millimeter coil with a 4 mm sample inside of it at a not at equal angles. So your sensitivity and your ability to pulse at very good powers was pretty low, but spectroscopically your experiment is really easy. You just need a pi/2 pulse to get the isotropic spectrum. Okay, so we could do something else. We could spin at 2 different angles in the same experiment with the same spin. So we can change angle partway through the experiment. If we imagine the engineering required, we're spinning at one angle. We move the magnetization up to Z, so we're working with T1, so it lasts long enough for us to do this. We then change the angle that we're spinning at, put it back into the SY plane, and then do more spectroscopy. This experiment was dubbed dynamic angle spinning. It came out of the lab of Alex Hines. And in this case, you'll notice that neither of these angles is the magic angle. Either magic angle, so they're spinning at 37.38 for part of the experiment and 79.19. The reason for that is that it's just you only have to spend equal time on either side, and then you can create an experiment where you refocus the isotropic in the indirect dimension along an axis in this experiment. So you are applying just a series of pi/2 pulses and then an echo at the end. You have a pi/2 pulse, then you digitize a dimension. This is when you're spinning, at 37.38, and then you put it up, you put it along Z, you do your hop, you hop 79.1, then you wait a certain amount of time such that you spend an amount of time in up as you have down, so that you create echo here where you have pure isotropic spectrum. So you've eliminated your anisotropic interactions with this echo when you spent as much time in the P2 coast and the P4 coast in positive and negative dimensions. So we're essentially doing an echo in the spatial symmetry using these angles. And these angles are such that the echoes are simultaneous. Yeah.
You were trying to spin at a compromised angle, like minimizing both P2 and P4, but not both going to 0.
So you're talking about a variable angle experiment, so like a vast experiment. So people have done variable angle.
But it's an angle which tries to minimize both the second and fourth rank harmonics, but neither going to 0.
Yeah. So then you would have a powder pattern for both simultaneously. So you'd have to fit both tensors at the same time. So it'd be even more difficult. I mean, you could think about the experiment, but yeah. I mean, you could think about doing an experiment, yeah. I mean, the kind of experiment that you're thinking about, you would then have to come up with some pretty interesting spectroscopy to pry out what you're doing. But I guess the closest thing that I could think about is it's an experiment that exists called Coaster. So you actually generally, so it's a combination of off-angle spinning and MQMAS. So essentially you do a multiple quantum, but you're not at the magic angle, you're at a different magic angle. And so you're not at either magic angle. And so then you end up with a correlation of anisotropes in a 2D experiment. And so you get these cool looking shapes where they look like, circles and, in space, because you have anisotropy along one angle and anisotropy along the other.
Do you have the sense that there's much double rotation going on now? Like in
No. I think the experiment is logistically hard. No manufacturer makes them anymore. And so if the probes exist, they exist because somebody has maintained keeping them from breaking. So I think that it was just a very difficult experiment. And while it's really cool that you get an isotropic, you see how many spinning side bands you have. So as you get to complex samples, it becomes really difficult to prize out much information more than a 1D. So trying to do like more complicated 2D NMR is kind of out of the question. I don't think I've ever seen it. But then again, I just don't think there's very many of these in the wild that still operate. Like you can still spin them, you can still pulse them.
Were they doing that in Phil's lab when you were there?
No, he had one, but hadn't been used in probably a decade before I got there.
Do you
Kind of very
understand how the air hits the inner rotor? Like, what is that?
I don't know exactly how it works. I've seen them and they have a bunch of like kind of like Swiss cheese. Like the outer has some holes
Had a hole in it.
that basically funnel the air and then the bearings are inside there. So I don't know exactly how it works. I mean, you would think that if somebody was going to do something like this or try something like this, the person I would think about would be Dimitri Speculario. I could see him being interested, mainly because sensitivity is a big issue there. Maybe you can use microcoils. Maybe you can actually do that with this. I don't know. I don't know how easy it is. So there's a person, I think he's in Belgium now, I believe. Professor Dimitri, I think he moved to Belgium from France. Anyway, he does very interesting experiments. One of the experiments he does is a microcoil experiment. So you put a coil, you basically put your sample inside a capillary, wrap a coil around it with some RF, you put that inside your rotor, and then pack it, and you put that inside your sample, and then you use the inner coil to do your spectroscopy. So it couples to the coil in your probe, and so you get better sensitivity and much stronger pulses because you have a really small, tiny, sometimes like half a millimeter coil. They're fairly finicky because you're spinning RF inside your probe, inside the magnet, and if the rotor crashes or has an issue spinning, then you have to rewind a new microcoil. The microcoil has to be built specifically to the sample. But that's something where you could think about, maybe you could get better sensitivity if you could use microcoils to basically do coupling. So you couple the coil inside to the outer coil through the air as a bilateral thing. So what does this look like practically when we try to do it on an actual sample? So here's a sample. This is LMSG of oxygen 17. So here's just the MAS spectrum of it. So it's really broad. You're never going to get much information out of this, 600 megahertz. Then we do double rotation, and you can see here that they spun at 2 different spinning frequencies, so that they can identify the spinning side bands versus their center band peaks. If you spin just at one, trying to get the spinning side band out of this blue spectrum would be very difficult, even out of the red one where you saw the spinning side band here. But you're limited to probably 1 kilohertz, 1.5 to 3 kilohertz. You spin at those few spinning frequencies, and you can look and find the isotropic peaks in your spectrum. In the case of your dynamical spinning, you get a 2D spectrum, so it's not just a simple 1D. We're doing 2D spectroscopy. We've correlated an MAF dimension, spinning dimension to an isotropic dimension here, and then you get 5 different oxygen sites in topside silicate. And so in each one, you have an isotopic peak, and along each dimension, you actually have the MAF spinning second order quadrupolar interaction that you can then fit out. So you get a little bit more information from this dynamic spinning experiment, but obviously because it's the 2D, it requires a lot more acquisition time and scans to get the same isotopic information. Okay, well, we're NMR spectroscopists, we're not engineers, so let's use spins to do it instead. And so then Lucio Friedman came up with this really interesting experiment that if you're really clever, you can find a solution that doesn't need intricate engineering, because as I said, we're spectroscopists, and we also want to use a probe that came with the instrument instead of some other probe that we have to build ourselves in the lab. So now we're going to design an experiment that uses echoes to refocus the interaction similar to the dynamic angle spinning experiment. But instead of just using regular old transitions, we're going to use formally forbidden multiple quantum transitions. So we're going to just hit it really hard and hope that we can get some out of this. And so he came up with this experiment that's called multiple quantum MAS or MQMAS. And so in this experiment, in this 3-pulse version of the experiment, you can do just 2-pulse version, but in this 3-pulse version of the experiment, you first excite a multiple quantum, here a 3 quantum. So a lot of times you might see this called 3QMAS. In a 3-half nucleus, that's the only one you can do. But in a 5-half nucleus, you can do 3QMAS or you can do 5QMAS. So you can do the triple quantum excitation, or you can actually do 5 quantum excitation to start off with and then reconvert. Obviously, the higher the quantum is, the less likely the transition is to occur, and so the less signal you're going to get out of the experiment, but the narrower the line. So you're going to excite a triple quantum or multiple quantum transition. You're then going to flip it back around and reconvert here to the +1, and then we're going to use an echo to get better lines. All the reasons why you use echo. So how does this work practically in space? So we're going to excite this. I'm going to wait T1. This is going to be our digitization in the indirect dimension. So we're going to digitize. We're going to reconvert back. Then we're going to do an echo and come back. And what happens is that we get an echo along the pathway, the transition pathways. So I have them on here. So the P pathway, our echo is happening here. And this one, our echo happens out here. And then we have an echo that happens here. And they're all going to depend on how long they spend in this multiple quantum transition here. So they're going to move with time non-linearly together. And so you end up with a spectrum where along T1 and T2 space, you have various different pathways eliminated. And this is the one in green we're interested in. This is the one that's not eliminated by NAS. So the other anisotropic interactions are already spatially being eliminated in a way. And so then we do some clever processing, post-processing our spectrum, and we move this axis, move the space of our experiment such that this C4 removed axis is along T1 prime and T2 prime, and then we have a space that gives us our interaction. This is an affine or shearing transform. So we just apply a shearing transform to the data that moves things around. One important note on this is that there's a field dependence to all frequency axes in quadrupolar nuclei. It's hard to see in that aluminum spectrum I put up. Here I'm looking at rubidium 87, double angle, dynamic angle spinning experiment here, where we start out at 500. As we go down to 4 Tesla, you can see that these peaks, they move around. They're not static, so it's not in ppm space. It's not like an isotropic chemical shift spectrum of carbon, where you expect that peak at 200 ppm to be at 200 ppm, at 900 and at 600 and at 400 and at a gigahertz. You don't expect that to move around on you, and if it did, you'd be really concerned. This is a really important thing that you should almost never label a spectrum isotropic chemical shift if it's quadrupolar nuclei and solids. Even in solution, it shouldn't be labeled isotropic chemical shift, because it's not a chemical shift it's an isotropic frequency, because there's a component that is due to the quadrupole and a component that's due to the chemical shift. And so what you're seeing is the change in field dependence of the isotropic quadrupolar shift, which has a 1/omega naught dependence. And as you can see, it creates these funky things like maybe all these peaks are not in the same order at 4 Tesla and 11 Tesla, and in fact they're not. And that depends on how large their CQ is. So there's this CQ factor, and the isotropic shift that you see is the isotropic chemical shift minus 1/40 times CQ squared over mu naught squared, and the CQ is CQ, and it's basically a measure of your EFG. So depending on how large the EFG is, it might have a different slope than the other ones in your spectrum. So you'll actually get level crossings between, not really level crossings, but you'll get frequency crossings. So you can't necessarily trust just that like this is like 1, 2, and 3. Like this, it's not necessarily 1, 2, and 3. It might be 1, 3, 2, going across the spectrum. Okay, so we're going to talk a little bit more specifically about oxygen 17, because this is what I did, and I have like some examples of how this practically works. So in oxygen 17, you have a bunch of different sites, just like you would in anything else. So you can think about this like what you have in C13, and they're all going to have varying amounts of shielding and quadrupolar interaction. So say you have like a hydroxyl, you've got a CQ that's around 9.5 or 8.5 to 9.5 megahertz versus something like this C9 nitroso, which can get up to 15 megahertz, and you might have a 3,000 ppm CSA on top of that. So talking about things that are very difficult to try to look at versus they don't have so like a phenol, which is 8.5, and only in the hundreds of ppm. That's something that's much more accessible as far as what you can do. And so then obviously they also will have has a very large chemical shift range over hundreds of ppm. So it's a really attractive nucleus if you want to do spectroscopy, because we have a very broad range of chemical shifts. We can really well isolate different types of oxygen 17 sites in a spectrum. We just have this pesky problem of broad CQs. So oxygen 17s of the same sort of environment type are going to be fairly narrowly distributed. So this is data on sort of the 5 different sites that you'll see in most biological molecules. You'll have the CO and NCO, and then this is the CO of carboxylic acid. Then you'll have the OH of the carboxylic acid, which is over here. Then you have your alcohol, and then you have water, and they're fairly well resolved if we can go up to 1.3 gigahertz. But if we're 500 megahertz, you have just one of these sites of each, and you have this very broad spectrum at the top. It's hard to isolate. But if we get down to the 900 megahertz, then we're talking about something where maybe we can do some spectroscopy here. And inside each one of these site types, you can see that there's still a very broad range of isotropic frequencies. These are fit chemical shifts, actually. So they're fit out of the simulation, the chemical shift, rather than just being isotopic frequency.
So chemical shifts.
Yeah. They come from this paper, so they should be chemical shifts. They come out of fit, so from simulation. So that's what the input parameter of the simulation is, chemical shift, and the frequency is included with the EFG part of that. And so you can see that you have something around the 60 to 80 ppm, 40 to 80 ppm chemical shift range, even within say these amide carbonyls, which tells you that if you had the ability to look at the isotropic peaks in a protein, you might be able to isolate each individual peak even easier than you can for a carbon-13 on the carbon. Okay, so but how do we practically look at figuring out what the CQ is and what all of that is? Well, we use spectral fitting generally to do this. So you can do this in multiple ways. You can use a full spin system simulation of a time length, something like Simpson or Spinach, spin evolution, gamma. You could write your own. We will go in. You could write your own equations if you wanted to. That was really what you decided to do, and do a full time length simulation. You can also use programs specifically designed to replicate the frequency domain signals. So there's some of these DMFit, FFmate that are out there in the wild. You can also write your own code to do the math and figure out the power pattern fits. And it's really helpful to have multiple magnetic fields. As I said, there's a 1 over omega naught tendency of the spectra, and so it's really important if you have a spectrum that has some overlap, take it at a different field, and the peaks will move, the shapes will change slightly, and you'll get possibly more information by fitting simultaneously multiple fields than you can from a single field spectrum. Okay, so what does this look like if you're trying to do something practical? Well, one of the first things that I did in my PhD was I worked with a postdoc, Vlad Michaelis, and we did oxygen 17 in bound water environments and amino acids. This was an area, if you notice that chart a couple of slides ago, that this review paper didn't have, there wasn't much literature on what happens if you have water that is strongly bound, hydrogen bound to your sample. There's a few examples, there are a few examples in materials literature of these waters, particularly ones that have been studied, ubiquitously for deuterium and hot sort of studies, but there wasn't a lot on the oxygen 17. And so we decided to take a look and say, well, this should give us a chemical shift range. We should have something interesting to say. And so we took and we, labeled the oxygen 17, oxygen 17 had oxygen 17 labeled a bunch of these amino acids. So we had, a few of them, and here I'm just showing a few. And you can see that there was a fairly good dispersion of isotropic chemical shifts, about 40 ppm range. But there was this really interesting issue that all of them had almost the same quadruple coupling constant and asymmetry parameter. You can see it in the spectral. All the spectral look pretty much the same, just shifted. And here I'm plotting the isotropic chemical shift, fitted isotropic chemical shift on the spectrum, and you can see that it's not very good. A lot of times in quadrupolar literature, you'll see people, if they don't have a good enough line shape, fit like a CQ to it. If you have like just a broad line and it kind of looks Gaussian, or there's a little bit of shape, but it's not enough for you to actually fit something under it. It'll report center of gravity shift of that width, and then some sort of breadth to give you an idea of a large depth of CQ. But the center of gravity shift of these would be somewhere in here, but the isotropic shift tends to be toward the left edge of these spectra. As you get higher and higher in the field, the peaks will basically move toward the isotropic shift. So they'll narrow from this direction. The isotropic chemical shift is not going to change, but the quadrupolar shift is dependent on that field. So
What did you say was the V naught and the frequency?
oh, in these experiments, the V naught was likely 750 megahertz, and we're probably spinning around 15 or 16 kilohertz, something around there, maybe 20. So these were in 3.2 millimeter rotors. So actually probably 20. And they were either 750 or 900. We did experiments of both. I don't know exactly which ones these spectra came from, but we did both 750 and 900. Multiple fields to help it.
Yeah.
Okay, so what's going on here? Well, we looked into it, and our first thought was this doesn't make any sense because there's hydrogen bonding, and hydrogen bonding should have a very large effect on the structure of the water, and EFG is very sensitive to structure in every other case that we've ever looked at. So here we did quantum chemical calculations predicted using the STPAW method, which has been done extensively with oxygen 17 at the time. It was shown to be fairly predictive, and you can see that we have an experimental CQ that isn't moving, but this calculated CQ has a 2 megahertz breadth, and similarly, almost no change in the experimental asymmetry, and yet the calculated asymmetry spanned almost half the range of possible asymmetries, as you would expect from hydrogen bonding. And if you just took the calculated CQ's eta, there was a strong correlation to hydrogen bond length. So the O to in bound length had a strong, and those H's, they had a strong correlation to the calculated values as you'd expect, but here the external values are giving us nothing. So here's what I'm saying. So that hydrogen bond length has a very strong correlation to the calculated CQ and eta values. So you'd have expected something similar in our experiment values. What this is saying, our experiment is saying that there's no difference in the hydrogen bonds of all those brown waters. They're all the same. which doesn't seem like it. So something else must be going on. So we took and we went to a sample that, was a little play favorite of Bob's, barium chlorate monohydrate. So he did a lot of deuterium NMR on this sample. It's a fairly simple monohydrate, and it's not in an amino acid, but it's fairly well characterized with lots of different spectroscopies. So this was our go-to. So we took an NAS spectrum, we took a static with proton decoupling, and we took it without proton decoupling so that we could look at all the different interactions in there and try to fit out all these different interactions we have on the molecule here. I put the dipolar OH, then you have the CSA and the EFG tensors displayed on the molecule. And so you got similar parameters as the other hydrates at ambient, room temperature, CQ around 6.9 and eta just about 1. So you can see this quite a sharp pattern. And so then the next thing we did was, well, what happens if we cool it down? Because there was NQR, so this is one of these. So this is a nuclear quadrupole resonance spectroscopy done at 0 field. So this is the type of spectroscopy where you just measure the CQ value. If you basically you do NMR, but you're not the magnet on a quadrupole nucleus, and you can detect the CQ, so you have very little resolution, but you can detect the CQs. And way back in 1976, these people had done this at 77 Kelvin, and they came up with a CQ of around 7.6 hertz. And so we thought, well, maybe it's just temperature. Maybe if we get cold enough, we would get the quantum chemical calculation value, because the quantum chemical calculations are done at 0 Kelvin. So there's no dynamics in those calculations. They're done as though there's no movement in the molecule at all. So what we did was we took the sample and we cooled it down from our standard 300 Kelvin. We had our standard values. As we cooled down, we got down to 170. We measured this spectrum, so you can see the spectrum looks a little different. And I'm highlighting with some vertical lines to show sort of isotropic edge of the power pattern. And then this red, the right edge of the spectrum at room temperature. And then as you move colder and colder temperatures, this right edge gets further and further away from the left edge. So you're getting a broader and broader spectrum. Underneath the dashed lines are just the fitted values for fitted spectra. And so you can see that we went from 6.9 down to 7.4, and at about 105 Kelvin, we got 7.55 and a 0.92. And so you can see the asymmetry parameter is also moving further and further away from unity here. And so what this told us was there must be some dynamic that's happening that's causing an averaging of the quadrupolar coupling in the quadrupolar tensor in these hydrates. And that's why we don't have a very good grasp on the calculations. And so what is this? Well, it's not the twofold hot that you get in deuterium. So in deuterium, you study the twofold hot about this axis, but that the VCC is invariant because it's coming straight out of here, so it's not changing when you flip along that axis. So it's not hot, which makes sense because we didn't get just half the CQ value of the expected. We got something else, and so it actually turns out that there's these vibrational motions, these swifting, waving, and rocking motions that were studied, back in the 70s and 80s, using different types of spectroscopy on the sample, where they showed that they did averaging in these, they looked at these modes. It's actually just 2 of the modes that affect, this. So you have this, I think, twisting and rocking, that, the waving and twisting. Rocking does affect it. Rocking is along, is moving the other things all off of VCD. At least it doesn't affect the CQ. It might affect the asymmetry slightly. I would have to look into that to see how averages that affect the ROI. We were primarily looking at that component. So one other thing that I didn't note here, but it's kind of important, is that at room temperature for these oxygen in water, we didn't have to do any proton decoupling. In these spectra, however, we went down to low temperature, we got this very strange looking spectrum with this extra horn. This is all due to this bringing back, so the twofold hop eliminates basically averages the dipole coupling such that in the oxygen 17 spectrum, you don't need to do any decoupling. It already basically self-decoupled. If you apply proton decoupling, it doesn't do anything at room temperature. But if you get it cold enough that you stop the hop motion, so 100 Kelvin, no more hop, you get this strong horn from this triple interaction that's happening here and with the quadrupole. It's a very interesting phenomenon, but we were able to fit it out. To fit this spectrum requires you to have a handle on the geometries of, the HH, the DH, the CFA, and the FTD all have to be properly aligned on the model, like with respect to one another. Otherwise, you move the angles around and get a different looking spectrum. And here's just a gamma simulation that one of my colleagues did at the time that showed, if you put in all of this that we found and you do hop, if it exchanges slowly, you get the spectrum expected. As it changes faster, you get this more. Until you get up to very, very fast motions, you don't get the spectrum sort of at room temperature. You actually end up capitulating a spectrum where these two shoulders are the same height, which if you look back is more similar to what's happening here. So they're very different heights, and then when it's cold, they're also the same in between. They're kind of looking sort of in between, which is good evidence that that change here is due to that hop being in a intermediate motion. Okay, so what happens if we have multiple of these bound waters? So in all of these cases, we were looking at monohydrate, so we only have one water to worry about. What happens if we have more? Well, we took this magnesium nitrate, which has 24 waters in its crystal structure, broken down to 4 different water sites. If you look at it with some simulations and some calculations, you get 4 different distinct water environments. And the question was, can we isolate 4 distinct water environments in the NMR? And we were able to, using MQMAS. This is all triple quantum MAS, and so you have your MAS frequency here. Our initial spectra at 900 megahertz. There wasn't. You only saw 3 sites at a near 1 to 2 to 1 ratio of the sites. And it wasn't until we took spectra at slightly lower field and at higher field down in Florida that you could resolve all 4 sites in the spectrum. And it actually turns out that, when we fit them all, and it turns out what was happening here. So we could see that we had, and we were able to fit environments to all 4 of them using the 2 fields that we have. And it actually turns out what was happening is that once again, we had a flipping of the sites, and 900 megahertz happened to be the worst possible field to have done that, which is what we did at first. And we only had the 3 sites, and we were pretty disappointed with that. But then when we took a very high resolution spectrum, so this is just digitizing way more in the indirect dimension than we ever did at MIT on the 900. We never went back to take the spectrum again after we sent it forward. So both the 800 and the 1.5 gigahertz spectra were taken at the National High Field Lab by my collaborators, Ivan and Zhang Gong. Just the data. And so you can see that this is calculated and this is experimental shift values. And so you can see that these 2 sites in the middle, site 2 and site 3, flip over each other based on the slight difference in their CQ and eta values. The PQ is slightly larger on this site 2 than site 3. It's a stronger slope. And so you get this crossing, and it just happened to be that we picked a field where the crossing, where the 2 peaks were at their closest together. And so isolating in the 900 was not going to be possible. As you can see in this, in the experiment, they're obviously each other, but even in the simulation, those are right on top of each other. They're not going to be looked at. Okay, so then what's the next step with oxygen 17 or any centigrade 1/2? Well, we want to do correlation spectroscopy. Reverse spectroscopy. We want to correlate it to something else. We don't just want to look at the environment of the oxygen. We want to look at the environment of the oxygen in comparison to, say, nitrogen or carbon or protein. And so you can either do kind of two things. You got to drop that soup of different things. You can do cross-polarization. You can do read-or, feed-or, read-or, trap-or. There's millions of these. Some of them are specific to quadrupolar nuclei and work a little better, such as read-or and trap-or. They're probably not ones you've probably heard of, but there are variations on read-or and feed-or where you do a specific type of pulse on the quadrupolar nuclei to try to boost the sensitivity of the experiment over just traditional hard pulse. So some shape pulses at much higher fields, offsets, stuff like that. You can also do dipolar-based HMQC and HFQC experiments. These have proven more effective than cross-polarization in a lot of ways to do detection, either proton detection or transfer from protons to your quadrupolar nucleus. The one thing about cross-polarization or any transfer from a proton to a quadrupolar nucleus is a lot of quadrupolar nuclei tend to have much faster relaxation time, so faster T1s than protons, so you lose that advantage that we have in solid state. Wanting the proton T1, you get the enhancement of the signal plus an enhancement of how fast we can rep. In general, for the oxygen 17, my T1s were on the order of hundreds of milliseconds, so I could rep the experiment as fast as I wanted. For direct oxygen, if I wanted to do a CP, the sensitivity was much lower because the transfer is not very good, so you don't actually even get a one. You usually get a fraction of your direct attack signal in a CP. The advantage there is that you're only looking at sites that are close to the proton, so there can be some advantages in why you want to do it. So how does this work? So this is the Reed-Door experiment that I was talking about. So it's a rotational echo adiabatic active double resonance. So it's like Reed-Door, but instead of just a pi/2 pulse, you apply a pulse that has 1/3 the length of the rotor period on your quadrupolar nucleus, and always apply your pi pulses not on the quadrupolar nucleus because the more pulses you have on your quadrupolar nucleus, the more interactions it spreads out to, and you end up losing your signal. So if you try to do something where you do the sort of read-or, feed-or, where this is the one where you're applying pulses, you're probably gonna be able to stab with your signal. And so then in this case, we're looking at something here. This is a dipeptide and acetyl VL. And so we have oxygen on these three sites here labeled at 70%. And so we're able to look at the different oxygen nitrogen interactions in a Reed-Door between the nitrogen of the valine and the nitrogen of the leucine here and fit it each one of them to different distances. And
that experiment. So you have both oxygens in the same molecule, or
yeah, so with all three oxygens are in the same molecule. Yeah.
and like what percentage would it be?
70%.
Oh,
Or 70% O17 label.
Wow, okay, and you're reading out on
Nitrogen. Yeah.
And
Yeah,
is
we have
that
two-
better than carbon? To do?
We did carbon as well.
Oh,
So
sorry.
we did nitrogen. 'Cause nitrogen is the one that's directly involved in hydrogen bonding. So
Huh?
we wanted to be interested. And also, we have a really cool probe that can do H&O experiments, and those are pretty rare. So we wanted to utilize that.
It is.
So you can also do a similar thing on carbon, and you can do T-Door. So we did T-Door, so we can actually look at 2Ds. In this case, so here we have our three oxygens. They're labeled at about 70% O17.
Oh, wait, who made that? Who made the O17 thing?
Mike Coleman and I did.
You synthesized it,
We labeled it. Yes.
starting from water.
Starting from water and protected amino acids. I'll go over the labeling experiment in a few slides. I should have done it first, but I
No,
had the slides jumbled a little. So in this case, for For the T door, I actually found that putting all the pulses on oxygen was better. I know I said don't do that, but then I did it, so, doesn't always work. The T door experiment is, particularly this DF door, it works a little differently. So because of the out and back, it actually worked out that if you put a pulse up there, just one the oxygen, it didn't work very well. Also, that's the way the experiment's designed, so we can come back to carbon detection. And so in this experiment, then we were able to look at the different carbon, C alphas and COs with respect to the different O17 labeled peaks, whether it was the peak here, and in fact, this one is shown because distances are long enough that you don't really see it. And this transfer, for whatever reason, is very inefficient. I'm not sure exactly why, but for whatever reason, because that peak would be up here, but it didn't really exist. It was just too weak, I think. Okay, and so then you can do the same thing where you then do, a build-up time, and you can fit here showing, distances between these different interactions. So in this has been a 1D. These are 1Ds on the carbons, not the 2. It's not. We didn't do this many 2D experiments. They take a very long time for 2D playing. So you do need to include this OH distance to fit the leucine build-up time. So there is transfer that's happening there. It's just not, for whatever reason, either the oxygen is 2D or I don't know what's going on in the 2D, but it never really showed up. But this 2D is I want to say it's something of a, 5 or 6 day experiment. So we didn't get too many shots at trying to fire it. Okay, and so then you can think about doing even different things. Like we looked here to do proton detected experiments. So we did this proton detected R cubed recouple the net experiment. So you start on oxygen, you knock it down, and then you do this net dipolar mediated net transfer, and you can look at the oxygen 17 dimension, which is this one here, and detect proton spectrum. This is just a 1D spectrum that you get out of it, and then if you do it in 2D, you can see 3 different transfers happening. One between this OH, one between this O to this H across, and then the same similar, the carbonyl OH to that carboxylic acid proton peak. And so you can see those intermolecular peaks happening in that spectrum. Okay, but we still want resolution. So what you really want is resolution and sensitivity because we want it all. And so you can apply a multiple quantum in front of this experiment. Think about getting narrow peaks in both dimensions. But as you can see previously, this was not a very highly sensitive experiment, and the MQMAF is only about 2 or 3% efficient. You have about 2 or 3% of that signal once you do that, and then you have to across beyond it. So we weren't quite able to get there. Okay, so here we go. Label it. We need sensitivity. We need to label it. The natural levels of oxygen 17 is about 0.04%. So we're not going to do much in solid state with that at natural level. And so this was the reaction that we used to label. We got it from a paper that did oxygen 18 labeling for mass spec and vibrational experiments. Essentially, you start off with, so historically, most oxygen 17 labeling in amino acids happens using acid catalyzed exchange. Basically, you take your amino acid, you put it in strong acid with O17 labeled water, and you boil it, for 24 hours, and then that's it. That's pretty harsh. We don't want to do that to proteins. We don't want to do that to any other sort of sample that we actually care about. It has to come out the other end and still be sample. And so this uses FMOC protected amino acid. And one of the reasons why we like the idea of protecting amino acids is starting to be protected for doing peptide synthesis later on. So we could take this directly to a peptide synthesizer and make peptides off the amino acids that we labeled. So what it does is it uses this carbonamide activating agent, EDC, HCl, and a little bit of this acetic acid, but it's not that strong. And then you add the water, and you basically just run it at room temperature for 18 hours, and then you do this, and then you add more EDC, every 18 hours or so, 18 to 6 hours, something like that. And essentially, it does this multiple turnover reaction where it keeps labeling the different oxygens on the amino acid here, and it, instead of like acid catalyzed exchange, which usually tops out around 60 or 50 or 60% thickened. So if you put in 100% O17 labeled water, you'll usually get about 50% labeled amino acids, and mostly it'll be like 100% on one and not on the other, very little doubly labeled. In this case, you get about 90% efficiency, most of them. So then you get a lot of doubly labeled amino acids, not 50% of it being singly labeled on on one and then 50% on the other. And so that's how we were able to get this sort of 70% labeled. We started with 70% labeled water. We did this reaction for leucine and for valine, and we were able to get good labeling on the others. And since we've done this, other labs have been able to do different amino acids as well to get labeling. Okay, what else can we do? Well, we can try to do other sensitivity enhancements. Well, we use the satellite transition. We've got these other transitions, they have magnetization on them. Why don't we try to use them? So you can do these sort of experiments, the RAP, multi-RAP, DFS, hyperbolic secant pulses, Wurst pulses. All of these operate on far offset pulses that are broad and shaped, and that then help to equalize. The idea of enhancing this is that we're going to take and we're going to saturate these satellite transitions to create a much larger imbalance in between the central transitions. So if you saturate them, you get an enhancing factor of I plus 1/2 in your spectrum. In the case of this RAP, which came out of Phil Granadetti's lab, you apply pulses on either side with an offset on either side, 0 frequency. And if you do this multiple times, 10 times, you then basically try to saturate these satellite transitions in such a way that you get an enhancement, raft enhancement. You can do a similar thing with Wurst pulses or hypersecant pulse over here, and they're a little bit easier to do than this raft pulse, which operates a little bit more complicated. But it was a pretty early on experiment. There are other pulses were, and the raft just uses Gaussian pulses, so they're pretty simple pulses to work with. Okay, so what happens if we do this? So in this case, this is a paper that I did a few years ago on that same NADL sample. And so if you apply an off-resonant Wurst pulse, that's what this is in this diagram. You have this Wurst pulse off resonance, you're applying this pulse, the type of fault-shaped pulse that came out of Rob Turco's lab and popularized Rob Turco. I actually don't know if it came out of his lab or if it's out of Rod's lab, actually. I can't remember, but he used it most readily, I think, of everybody. And so you can do an experiment where you add this Wurst pulse and just do a CP, or you can do the DRNF, or you can just do a regular CP experiment. Carbon. So this is a proton and carbon CP, or you do an oxygen and carbon CP, and that's what these experiments are showing, that we can efficiently get a pretty decent transfer in a short period of time from oxygen 17 to carbon 13 transfer. And so you can see that these are much shorter experiments than the proton, and that's because we can wrap this, probably every 120 milliseconds or so, where they're applying our pulse. And so then you can think about other experiments that you can do then. You can do this OCH experiment, or an HOCH, HOC, OCAH, known as O, CO, CAH. So this is just all different transfers that it's doing. They look very complicated. They use a lot of shape pulses, but essentially you're just getting this OCH, you're getting just the oxygen transfer through via carbon and then doing proton detection on it. If you do it from protons and then the oxygen to the carbon to the oxygen, you can see that your signal noise is not as good because you can't wrap nearly as fast. Similar thing when you do the more complicated COCA and then H. So you're only seeing the COO to CO to CAH transfer pathway. So you're narrowing the number of peaks that you see. And so then you can then digitize these other dimensions and get these spectra here. And then if you apply after the worst pulse a NQMAS experiment, they define this using this bar at the top, so we have isotropic oxygen lines. Then you can get these narrow line experiments, proton detected. And here it is in the broad line and then the narrow line, isotropic heat, and this is the full MAS spectrum. And you can do a similar thing, and then be able to pull out the different oxygen peaks. So here's the kind of experiment I was saying. I wasn't seeing this one what's here, and you can see it's half as strong as that one, so it is weaker. Transfer, you can do a similar thing with nitrogen. Once you have the sample and it's well labeled, and you have a good spectrometer, you can start really adding a lot of pulses and things to it. And do this rep store so you can get the build up and measure a distance. And so the other things that are done with other nuclei, a big one with deuterium is this respiration CP. So you can do a transfer element between the spin half and the deuterons using this complicated pulse shape, and you can get a good transfer, adiabatic transfer to your deuteriums from the protons, and then you can do interesting spectroscopy with the deuteriums in an actual sample. Here's just an example that came out of Van Haan's lab years ago, doing deuterium carbon correlation experiments. And so other people, this came out of the National Field Lab, where they looked at oxygen 17 amino acids labeled into the bilayer in a protein, granzyme A, in the bilayer, and they looked at the different oxygens in the bilayer, inside the bilayer, doing the oxygen 17 NMR, and so you can see the different leucines and glycine. So they labeled specifically the leucines in that protein. Some more, oxygen 17 and deuterium work here, where they did fitting of different water sites, both via the deuterium, NMR, and oxygen NMR, looking at the dynamics. This is a study of oxygen 17 of yeast ubiquitin, where they did some NMR. And then here's a really recent paper that I ran across when I was putting this together that I want to point out. So somebody actually took and did using a slightly different but similar technique, using a ball mill to do oxygen 17 labeling. And this is a little bit easier because all you need is a ball mill and water. Just basically take your amino acid and just grind it up with the water and it transfers. And you get labeled, but just singly labeled O17. You don't get the double label. And so then, if you then add that to the N9 media with unlabeled amino acids, with your LB, and then you harvest it and induce it, you can get oxygen 17 labeled protein. Here, specifically, they just labeled leucines, so they have leucines, and they did it on E protein from COVID-19, FITSQ, and A, a couple of bacterial proteins. And so then they looked at the difference in those leucine oxygen 17 chemical shift in the different proteins, and you can see that the peak is different, but it's still low sensitivity, and so it's still working up to sort of.
This is the person I was saying we may have for a seminar at some point. She was a student in Klaus Schmidt's group. It seems very creative to me.
Yeah.
Yeah, who, I don't know her very well, but she's down in Florida.
Yeah. Yeah, no, it was interesting. I hadn't run across it yet. The sort of experiment I
Yeah,
wanted
just,
to
you
do
know,
in my PhD and never got to it. Okay, and then just a brief slide on the, NYXCC's capabilities for quadrupole nuclei in solid state. There's quite a few probes that can actually look at different nuclei combinations. At 900, we have 1.6, 1.9 probe heads for our Phoenix probe, which is shown here, that can tune all over the place. And so there's a lot of different combinations. On the back of 2.5 millimeter black box probe, there's few aluminum, sodium, and deuterium are the primary ones, and then lithium-6. At 800 megahertz, we have a tri-gamma probe that can do quite a few different combinations, HDO, sodium oxygen, aluminum oxygen, HCD, HCO, HC, lithium-6. And then at 750, we have 4 millimeter XY and an X probe that have wide tuning ranges. They can tune kind of all over the place. Our 1.9 also has wide tuning ranges that can do quite a few different nuclei depending on what mode you're in. And at 600, our DNP probe from Phoenix also has the same capabilities as the 900 probe. So there's a lot of different nuclei. If there's interest in, doing quadrupole NMR, we can do it here if we have the capabilities. So, thank you for listening.
Thank you, Eric. That was amazing. I just want to mention to people in the group, I asked them to push back the time, but we still have to kind of. Okay. And today, in group meeting, at a regular length, Yoni was talking about MD of KCSA and trying to predict T1. So if you feel like joining us online, you're more than welcome. Anyway, thank you. That was terrific. Each time I hear it, I get something additional. So thank you so much.
Yeah.